Dexterous bimanual manipulation is a challenging problem in robotics. We have recently developed a bimanual setup with 2 commercial hand prostheses mounted on splints and controlled via surface electromyography, allowing human subjects to perform dexterous manipulation in controlled conditions. In this video, we show that the approach can be effectively extended for teleoperation in a daily living environment, grasping, carrying, and using standard objects. The human-machine interface we use is completely wireless and consists of 2 Myo-EMG bracelets and 2 Vive virtual reality motion trackers for detecting the wrist pose. The overall weight of the interface is about 180 grams per arm. The teleoperated platform is a torque-controlled robot Toro with 25 degrees of freedom based on the KUKA LWR joints, 2 position-controlled joints in the neck, and 2 prosthetic hands with 12 degrees of freedom in total. The robot displays a compliant whole-body balancing controller that takes care of keeping the robot balanced even in the presence of unknown disturbances. We show here a collection of daily living tasks performed in real time with the human operator standing beside the robot. The operator is using only visual feedback to perform the tasks. We combine an incremental variant of ridge regression with random Fourier features to obtain a system that can robustly detect multiple hand configurations, including power grasping and finger pointing. This regression algorithm is used to predict finger forces and grasping patterns from myoelectrical signals. The initial training time for each action is below 30 seconds. For the experiment, the master system provides a stream of combined data at 50 Hz, which is processed and then transmitted via Wi-Fi to the robot controller. The displayed tasks require bimanual coordination for grasping and manipulation of objects of different sizes, weights, and shapes, as well as more complex tasks such as holding a cordless phone and dialing a number, or balancing a ball between the hands. Another task is unscrewing a lid to pour the content from the bottle into a pot. This task was already challenging with our previous human-operated setup, and here it is solved in a teleoperated scenario. From the control point of view, the execution requires a timely transmission of positions that are translated into suitable control torques on the robot side to let the operator achieve the required bimanual coordination. Fine manipulation requires high and precise reliability of the position and orientation of the robotic hands, and accurate and stable SEMG-based commands irrespective of the arm posture and wrist rotation. Prosthetic myocontrol is known to be unreliable due to changes in time in the myoelectric signal caused by factors such as perspiration, electrode displacement, fatigue, and kinematic configuration of the arm. This work achieves stable, dexterous force control by means of a nonlinear incremental method that provides both accurate prediction and adaptation to changing conditions. On the robot side, the multi-contact whole-body robot controller accounts for unknown perturbation forces that might destabilize the robot when performing the intended tasks, as shown here when opening a fridge. The controller creates a passive and compliant behavior for regulating the location of the center of mass, the hip orientation, and the poses of each end effector used in the manipulation task. The implemented demonstrator is a realistic testbed for prosthesis control for patients with upper limb impairments, as they lack proprioception and rely mostly on visual feedback to perform the tasks. The technique provides natural and reliable control of dexterous hands.